Hey everyone, welcome back to I Teach You Science. Today is the day. The June 2025 Earth and Space Science Regents has been released. I'm going to go through the whole thing right now. We've never done one of these before in a video like this, so I'm going to go through, look, you can see the whole test is here. I'm going to go through the whole thing. Not sure how long this is going to take me, so we're just going to go question by question, and as we go, I will rate the question on my subjective scale, and if I thought it was a very easy question, it would be like a 1, and a 10 would be like very, very hard. All right, so let's do this. If you took this test in June, you were the first person to ever take a Earth and Space Science Regents, official one. So props to you, and hopefully you did well. Let's see how it was. All right, number 1. Base your answers to question 1 through 5 on the information below and on your knowledge of Earth and space sciences. Some questions may require the use of the reference tables, which we have here. So if you want to, you can, do the question first. I will put the link in the description on where to get it. Or you could do the whole thing first and then watch me go through it. You could have your reference table out for you to follow along with me as I go and just pause the video as you see fit. All right, it says, be sure to record your multiple choice question on a separate answer sheet. We don't need to do that here. And record the constructor response questions in your test booklet. Okay, so our sun, a star. The Hertzsprung-Russell diagram was developed from star charts by 2 scientists in different countries independently of each other in 1911. It classified stars based on their surface temperatures, okay, observable color, and magnitude. Absolute magnitude is a measure of how bright a star would appear if all the stars are the same distance from the Earth. The brighter the star, the lower the magnitude value. So the brighter, the lower. Okay. Our sun is classified as a spectral class G star with a surface temperature between 5,000 and 6,000 K and an absolute magnitude of 5. Based on this information, complete the diagram by placing 1x to indicate where this is located. Also identify the relative temperature and relative absolute magnitude of the sun as it transitions to a red giant. Okay, so a two-parter. So listen, we'll do one at a time, not to get ourselves confused. So we need to go spectral class G, so that's here, between 5,000 to 6,000 K. So here's 4,000, here's 6,000. So we could assume 5,000's here, so between 5,600, 5,000, 6,000, probably like between those two purple dots. Okay. And then an absolute magnitude of 5 is here. So we're going to go here, and we're going to meet up in that area. I'm just going to go to the middle, because that'll be a safe zone. So I'm thinking here is a good spot, and it says place an X there. Okay. So there's my X. And then identify the relative temperature and absolute magnitude of the sun as it transitions to a red giant. So you could see the giants are here. So we're going to be going this way. So I need to know what happens to the temperature and magnitude as we go there from here. So you could see the temperature is going to drop because a star in this zone is 4,000. So this is going to decrease. And then the change in absolute magnitude you could see is we're going from 5 to 0. So we also decreased in absolute magnitude. So that question, honestly, that was super duper easy. So I'm going to say this is a 1 out of 10. Very easy. All right, here we go. We got a model here. The model below shows the layers of the sun and information about some features of each layer. So there's a lot of information here. What I'm going to do is I'm going to read the question first, and then we're going to come up here and try to figure it out. So model of sun's layers, showing the layers of the sun, which clearly there's a bunch. Based on the information in the model, which list of 5 of the layers are in the correct sequence to allow energy generated by fusion to eventually reach the sun's surface? Okay, so where is the sun generating fusion? You could see the core is where we have to start because that's all 4 choices. So we're starting in the core. And we need to make its way to the surface. So we're going to have to go from the middle all the way to the surface of the sun. Does anyone say surface here? Look, the visible surface of the sun. It says it there, photosphere. But corona is the sun's outer atmosphere. Okay, so we probably look, we're either going to end at the corona, the chromosphere. That's it, the corona or the chromosphere. So which one of those is more on the surface? Let's check. Corona, the sun's outer atmosphere, or chromosphere, the layer above the photosphere, where the density of plasma drops. I don't know what the better answer is there. Eventually reach the sun's surface. If you go to corona, the sun's outer atmosphere, I mean, it could be the layer above the photosphere, above it, above the surface. So both of those, let's just go to the middle and see how it goes. So we're going to start in the core, then jump out to the chromosphere, then to the photosphere, which is the visible surface. But if the chromosphere is above the photosphere, you can't go chromosphere, photosphere. It has to go photosphere, chromosphere. So this one's actually out. And then transition region is inside even more. So this is like not going to be the right answer. Okay, let's start from the core. We're going to go radiative zone next. So that's here. So that's 1 to 2. And then the transition region, the irregular layer that separates the chromosphere from the corona. Okay, that's possible. Then the photosphere, and then the corona, which is the out. This might be it. That might be it. Because that kind of goes in order. All right, let's try the third one. Core to photosphere. So we're going from the core all the way to the surface, back into the insides. So this is wrong. Then core to radiative zone. Okay, that's good. To convective zone, yes. To photosphere, this is the answer. 4 looks like it's going to go in the best order based on the diagram. So we're going to go with 4. This question is annoying because this diagram is not really clear. I don't really like it. It's a mess. So I would say this is like a 7 out of 10 difficulty because it's just so annoying. You know what? I'm changing my mind. We're going to give it a 6 out of 10. Because I feel like if I already jumped to 7, I'm going to say like this is a like annoying diagram. And listen, these are all my opinions, especially if you're an Earth and Space Science teacher watching this. You know, I'm interested to see what you think. You know, leave your thoughts in the comments about which question you agree with me on my ratings or you disagree and you think it's a great diagram. Maybe you think that. I don't know. All right, let's go down. All right, the model below represents the orbits of celestial bodies around our sun. The inset model shows some information about the region of the solar system inside the orbit of Jupiter. Okay, so it's just zoomed in. So here's the whole solar system, right? And then here's like Mercury, Venus, Earth, Mars, just like zoomed in because you can't really see it in the model. Easy. All right, what do you have to say? The table below shows the eccentricity of the orbits of Mercury and Venus around the sun. Mercury is more eccentric than Venus. So remember, if the number is higher, it is more elliptical. And this is more circular, right? And I don't know if we're going to need the reference table, but remember, you do have information right here about, people call it eccentricity, I call it eccentricity, whatever you want to call it. That shows them all. But I don't even think we need that. Place a check mark in the boxes to indicate the 2 statements that are correctly predicted by Kepler's laws. Okay, so remember, Kepler has 3 laws. The first law is all planets travel in ellipses. The second law is that the planet gets faster as it approaches the sun, or the star at the first foci, or one of the foci, because gravity goes up, which means velocity goes up. And Kepler's third law is that the further the planet is away from the star, the longer it takes to go around. Do you have to have those memorized? Probably. I would say you should definitely know Kepler's 3 laws. You don't have to know which one is number 1, 2, or 3, but I would know them. I mean, that's what the question is. So this is a pure content question. So which one? Oh, 2 statements that are correctly predicted by the laws. Venus orbits the sun at a constant speed. That would be wrong because Kepler says as it gets closer to the sun, it speeds up. Mercury travels faster in its orbit when it's closer to the sun. Yes. Venus's orbit is less elliptical than Mercury's orbit. That's true, but I don't know if that's going to be a right answer. The orbital speeds of both planets are affected by their masses. No, this is going to be affected by the distance of the sun to the sun. Unlike Venus, the eccentricity of Mercury's orbit prevents Mercury from having a moon. It has nothing to do with moons. So there's your 2 answers. So this is going to be a check and a check. So if you know Kepler's 3 laws, this is easy. So I'm going to give this a 3 out of 10. That was good. All right. Based on our solar system model, if a new planet was identified that orbited the sun at an average distance greater than Mercury, so greater than Mercury, but less than Venus, so we're like between, so we're here. So if you look here, Mercury, Venus, we're there. The average speed of this planet would be, so remember, this is Kepler again. The further you are from the sun, the slower you are. So it's going to be slower than Mercury, but faster than Venus. So we got to find that. Greater than Mercury, no. Less than Mercury, yes, but greater than the average speed of Venus. That's going to be good. Greater than Venus, less than Earth. We're not even anywhere near Earth. So this is going to be 2. So I'm going to rate this actually. Yeah, we'll do it the same because it's another Kepler question. So that's a 3 out of 10. All right, here we go. An observer on Earth sees phases of the moon, but the moon isn't the only solar system body to exhibit phases. Venus also has observable phases as viewed from the Earth. Venus's orbit around the sun is approximately 225 Earth days. The photograph below shows a moon phase and Venus viewed with unaided eyes in the night sky. The inset box, which we know is zoomed in, shows Venus observed using a telescope. Both the moon and Venus are in a crescent phase. Okay. Using our solar system model, construct an explanation for why an observer on Earth can see a cycle of phases for the planet Venus. In the spaces below, write the terms for A, B, and C. Okay. So just thinking right now, the reason you see phases is because the position of the object and you is changing relative to where the sun is. So the sun's hitting a different angle of that object, so you see it lit up in a different way. So Venus orbits the sun, circling blank Earth's orbit, inside. Right? So if you didn't know that, you would go here and you could see Venus right here is inside Earth's orbit. Earth's orbit is here, Venus is inside of it. So that choice was given in the diagram. So we could just fill that in. In about 225 Earth days. This means that Venus is sometimes blank Earth, while other times it is positioned on the other side of the blank. Why would they put B? This means that Venus is sometimes... It could be both of these, no? Can it be sometimes closer or sometimes farther from Earth? Does it matter? All right, let's just get C then, and we'll come back to that. While at other times, it is positioned on the other side of the sun. Remember, the phases have to do with the sun. It is this change in position that causes an observer on Earth to see phases of Venus. So, why is this here? Okay. Venus orbits the sun circling inside the orbit in about 225 Earth days. This means that Venus is sometimes blank Earth. Well, wouldn't it be both? Because it's an elliptical orbit, so wouldn't it be closer to sometimes and farther from sometimes? That's what I'm wondering. All right, so apparently, after finding out a little bit more about this, because I just paused and went and looked at this closer, this is referring to the side of the sun that Venus would be on. So if this is the Earth right here, it's saying, and this is the sun, it's saying since Venus is inside the Earth's orbit, sometimes it's closer to the Earth, while at other times it's positioned on the other side of the sun, referring to it like this. So if this was me, so the answer is closer to, but if this was me on a test, you know, I could be way overthinking this, but I think this could be either way if you don't add the context of C. So that's how I was doing. I was trying to figure out in order, right? Venus is sometimes closer to or further from the Earth in its elliptical orbit. That's my argument. So they really should say Venus is sometimes blank Earth relative to the sun, comma, while at other times it is positioned on the other side of the sun. I mean, it's just bad for me. Okay, so I would say, forgetting the grammatical issue that I have with this paragraph, this would be like a 4 out of 10. But in my opinion, this could be bad wording, and it could be improved. You know, like if this was this question could be better. It needs to be. It's a good question, but it's just I don't like it. All right, we're moving on. Base your answers to questions 6 through 10 on the information below and your knowledge of Earth and space science. Some questions may require the use of the 2024 edition reference tables. Okay. Modeling Earth systems to understand global climate. The geologic record shows a long history of climate fluctuations. Okay, fluctuations just means changes. As a result of many different factors, climate scientists study models of the Earth's motions, ocean currents, plate tectonic movement, and atmospheric composition to better understand energy flow in and out of the Earth's systems. Okay. Obliquity, the tilt of the Earth's axis, so obliquity means the tilt, has a direct impact on the climate. Earth's obliquity changes on a cycle that takes place over a period of 41,000 years. The obliquity is currently decreasing and will reach its minimum value of 22.1 in approximately 9,800 years. And it tells you that we're currently tilted 23.5. Okay. Seems straightforward. During the winter, which statement best describes the amount of energy Earth's northern hemisphere will receive and the impact on global ice formation when the obliquity is 22.1 compared to the present, which is 23.5? Okay, so essentially, we are tilted less. So we would be tilted less. So if, let's say, so we're tilted like this. So let's just exaggerate and say if there's no tilt, right? Seasons would be spring and fall the entire year. So that would be, so if you look at this, so this would have the northern hemisphere being more mild. So this is asking going from winter, right? So that would be down here. Well, actually, this would be the other way if it was winter. So let's just say we'll go over here. If this is the sun, this is winter time, right? So it's cold in the northern hemisphere. And then you're saying we're going to tilt less. So let's just exaggerate it again. We're going from there to there. So if it was normally cold and now we're tilted less, we're going to be mild. So we're actually getting warmer. So it would be Earth's northern hemisphere is going to get more energy. So this is right. So these are out. And if it's more mild and it's not as cold, we're going to have less ice forming. So that's going to be choice 3. So I would say this question is pretty tricky because they're saying to going from winter, and you have to really understand what the tilt does. So I'm going to call this a 7. I'm going to say this is the hardest question we've seen yet, in my opinion. It's tricky. All right, we're going on. Another factor climate scientists have identified that contributes to changes in energy flow in Earth's system is ocean current circulation. Okay, here's the ocean currents. And remember, we do have a page on this, right? So what you want to try to do is, hopefully, when you see a topic, it should trigger, oh, there's a diagram on this topic on the reference table, hopefully. The model diagram 1 and 2 show some information about circulation patterns in the currents. Point X and Y are locations on Earth's surface. Okay, so we're over here, X and Y. Wow, we got a lot happening here. So you could see cold and warm. So cold is the dark, warm is here. Okay, how currents work, diagram 1. So it's saying step 1, the sun heats the water in the tropics. We got warm water here. Water moves north and cools down, and then it sinks, and the process repeats. Then we got diagram 2, the influence of fresh water. Step 1, increase in fresh water from glaciers. Okay, so that would be great. Step 2, addition of fresh water makes the North Atlantic less salty, okay, lowering density. And then warm water can't move north because it's blocked. So they're saying increase fresh water, decrease warm water. That's what this is saying. And this is also convection here. I'm just writing some notes because I don't even know what they could possibly ask about this. Let's see. Which statement most accurately describes the influence of melting glaciers at X on the strength of the ocean currents? So it's saying, I mean, I would say the warm water can't move. So more fresh water is going to, based on this, slow down the current. More fresh water causing the currents to become deeper. I don't think it said much about that. If anything, look, it's less salty, lowering the density. So I don't think so. I think if anything, this lower density is going to rise. More fresh water causing the currents to weaken. That's my current option. More fresh water to the ocean causing the water in the currents to become denser. No. Causing the water to become warmer. No. So the only one that could possibly work is this one. Because the other three, there's nothing about depth. It says less dense, so that's out, and it says the warm water can't make it there. So this is 2. So I would say this is like a 4 out of 10 if you can read the diagram. I mean, this, to me, this is a lot. So maybe, honestly, if I was a student, this should be like maybe a 5 out of 10. This is, I mean, if you get something like this, you really gotta like look at each one and try to think separately. Like, what is that showing? What is this showing? That's how I did it. See, I just wrote down things about each one, and I was able to do it. Which statement most accurately describes the influence of present surface ocean currents on the climate of location Y? So let's just see where location Y is. So we're here. So if I go here, does that help me? Right, so I'm here. Greenland's at the X, so it's kind of like that landmass right there. So it's here. So that's location Y, and this is sort of where the X is. I'm on the reference table, by the way. I'm just like seeing if this is going to help me. Let's see. Location Y experiences warmer air temperatures with more precipitation. Okay, so this is what we have to know for this. If it's warm, there's more precipitation. Because warm water is going to be evaporating, making clouds, making more rain. So this could be the answer. We don't know. But warmer air temperatures is not going to be less precipitation. That's wrong. Cooler would be less. It's going to be the opposite. So it's either going to be 1 or 4. Now, if we go to that spot, you could see in location Y, it's got this moving past it. The dashes on this, which is a warm current. So this is going to be warmer air. I mean, warmer water there too, which is going to influence the climate of the area. So I'm going to go with warm. Is there anything on this chart to help? Yeah, see, it tells you there it's warm. So we're going to go with that choice. Location Y is going to be warmer with more precipitation because of that. So I'm going to go with a 5 out of 10 again on that one. Kind of hard. If you didn't know that part, that warm brings more rain, that could really screw you up. All right. Since the Industrial Revolution, deposition of dark particles such as dust, dirt, and rock in glacial ice, contaminated snow, have caused glaciers to darken. This has led to feedbacks that have caused changes to other Earth systems. Okay. So glaciers are darkening because of dust and dirt from pollution. Percent of sunlight reflected and absorbed by different glacial surfaces. So if it was light, it's going to reflect. So dark is going to absorb. That's like the main thing that I would know. So if it's dark, it's going to absorb more. So we're going to get more melting of the glacier. So you could see like incoming sunlight is 100%, 90% is going back out off the fresh, clean snow. We got contaminated snow is 60% going back out, as opposed to the clean snow is 70. So more is getting absorbed. That's what it's getting at. And look, yearly and cumulative ice loss. Look, ice loss, higher number at the bottom. I don't know why they had to flip the graph just to make it more annoying. But you could see yearly ice loss is 0, and then over time we're losing more ice. So we're going to write losing ice over time. Which model correctly represents the feedbacks that occur when dark surfaces are exposed in glacial areas and cause the changes? Okay, so this should be pretty easy, honestly. We'll see. Increasing in dark surface area on glaciers. Okay, we're starting with that no matter what. Increase absorption of energy from the surface. Increase absorption of energy from the surface. Increase absorption of energy on the surface. Increase absorption. Okay, 1 and 2 are both the same on all of them. If there's more energy absorbing, we're going to get more melting. So this is out and that's out. And then if there's more melting, there's less ice. Oh my god, that was so easy. I'm going to say this is a 2. That was really easy. Any other ones for that? Like, here's my thing. Like, they had these 2 giant pictures for that one easy peasy question. Okay. Computer-based global climate models are helpful tools for collecting data on projected future climate conditions. These models use various scenarios or possibilities that assume different human-based decisions on how we address greenhouse gas emissions. The graph below shows future greenhouse gas compositions for 4 different greenhouse gas emission scenarios. Okay, so they're pretty much saying projected greenhouse gas concentrations. So A, this is going to be going up. B, it went up. C, it went up and then like stayed the same. And then D kind of went up but then went down. That's me just reading the lines. Okay. The graph below shows some information about the surface air temperature changes. Okay. So in scenario A, the air temperature went up a lot. Scenario B, it also went up. C, it went up. And D, it kind of went up and then stayed the same. Identify the numerical values for the projected concentration of greenhouse gases and for the approximate future change for the year 2100 Using scenario B emissions. Okay, so we're only doing B. So we don't care about A, C, or D. Do we need this chart too? Okay, so look, this is so easy. 2100 CO2 equivalent of B is about 800 parts per million. And then B for air temperature is going to be, this is 2.0, this is 3.0, so that's 2.5, and we're under that, so 2.4. That was so easy. So that was like looked like it would be hard, but it was actually so easy. That's a 2 out of 10. Now I just want to pause for a second. We just finished question 10, and look at the timestamps to see how long I've been explaining this. These questions take way longer than the old Regents. I don't know if you've ever done an old Regents, but they're just way more wordy, way more tables to identify. So you kind of got to go slow. You got to really see what's going on and draw back from what you learned in class and try to figure it out. Like, this is not a fast exam. It's just not. That's how they built it. All right. Base your answers to question 11 through 15 on the information below and on your knowledge of Earth and space science. Some questions may require the use of the reference tables. Okay, so far we have not used the reference tables. I mean, we sort of did here, but we didn't even need it. The carbon cycle. The global carbon cycle refers to the movement of carbon through different storage phases or reservoirs on the Earth. Reservoir is just an area where something is stored. Carbon moves through these reservoirs at different rates. Most carbon near the surface cycles fairly quickly. Okay, so the surface, it goes quick. Carbon in the atmosphere goes in about 3 to 5 years, while plants recycle carbon in about 50 years, so they seem the slowest. The carbon found in soil and fossil reservoirs is recycled in about 3,000 to 5,000 years. Wow, that's a long time. Okay. The carbon cycle has 2 parts. The fast cycle involves the biological processes of photosynthesis and decomposition, and the slow cycle is in the soil and the rocks. Okay, so things that are alive can, go through it faster. Wildfire events contribute to the carbon cycle. In 2020, mega fires released an estimated 107 million tons of CO2 in the atmosphere, equivalent to the amount released by 23 million cars. Okay, so wildfires did a lot. Model below shows information about these systems and the carbon cycles. Okay, so essentially what this is saying, humans have an impact. Carbon cycle. 2. We impacted too. Okay, so you can see. The model below represents how carbon levels change depending on what is happening with the trees in a forest. So forest carbon level. So it's the lowest when the carbon releases from fire and the carbon release decomposition and storage in dead trees. Carbon uptake and storage regrowth. Carbon uptake and storage regrowth. Okay. So it's saying there's less carbon in the trees when they're on fire. Okay, because it's putting all of it into the atmosphere for the most part. So less here because the line is lower, and then more here and more here when they're growing. Okay. Explain the process that the trees in a forest use to make energy for food. Seriously? Okay. And describe how this process is responsible for a decrease in CO2 levels. Okay. So, unfortunately, this is a biology question. There is a standard in Earth and space science about photosynthesis, though. So, I mean, I don't know why they put it in here, but it is. So, the process is photosynthesis. And it's important because it removes CO2 from the atmosphere to make energy for the food. So you know how plants work, right? They bring the CO2 in, and then they spit out oxygen, and they make their own food. So that's the answer to this. So honestly, it's really, really easy question if you know how photosynthesis works, and I feel like you learned photosynthesis in like elementary school. So as long as you like knew what it was, you could definitely figure that out. The model below shows the movement of carbon through the 4 spheres of the Earth. The numbers indicate the amount of carbon naturally added or removed from the spheres in gigatons per year. The numbers in bold indicate the amount of carbon added or removed by humans. Okay, so bold is humans. Numbers in parentheses are the amount of carbon stored. The parentheses is stored. So we're adding here. We're adding here. We're adding here. Oh no, we're adding here. We're removing photosynthesis. And then we're adding human emissions. Okay, this is a lot. I don't like this graph. Like the parentheses, Okay, let's just see what it says. Which statement correctly identifies the quantitative, which means numerical, cycling of carbon between 2 of Earth's spheres as a result of natural processes and human activities? Oh boy. Okay. Fossil carbon releases 2300 GT. So let's just see if that's true. So here's fossil carbon. While microbial respiration and decomposition absorbs 60. No, because fossil carbon's 10,000, so this is just not right. The deep ocean stores 36,000 more than is released by air-sea gas exchange. So 36,000, so this is 37,000. So if the deep ocean stores 36,000 more, that would mean that 1,000 has to be released by air-sea gas exchange. And as you could see, it's only 90. So this is wrong. Wow, that stinks. Human emissions add 9 times more carbon to the atmosphere than plant respiration. Okay, let's see. Human emissions, 9 times more carbon than plant respiration. But it doesn't say if this is multiplying. It just says 9 compared to 60. So that's not right. Which is the same amount released to the atmosphere by microbial respiration and decomposition. Where's microbial? That's 60. That's wrong, because then this would have to be 60. The amount of carbon that leaves the atmosphere, hopefully this is right because I eliminated 3. The amount of carbon that leaves the atmosphere and is absorbed by the ocean is 92. Look, atmosphere to the ocean, 90 plus 2 is there, which is the same amount that's released by the oceans back into the atmosphere and stored by ocean sediment. Look, released from the atmosphere, 90 plus ocean sediment, 2. There it is. This question is terrible. Like, why? That's all I'm wondering. Why? Why? Like, I'm floored about this question. It's stupid. I'm like, this is the worst question we've seen so far. Horrible. What are they testing on? You know what I mean? Like, what were they going for here? This just goes to show how disconnected whoever's writing these tests. This is terrible. So, in terms of difficulty, honestly, if this was a student, and I'm imagining a normal student, I would say this is a 10 out of 10. No joke. because of how stupid it is. It's a terrible, terrible, terrible question. It should not be on the test. And that's all I'm going to say about it. Garbage. Let me know what you think. So far, I'm going to keep track of the ones that I absolutely hate. So number 12 is terrible. All right, let's keep going. Oh my God, there's more to this question. Which explanation describes how climate change from increased atmospheric carbon dioxide has influenced human activity? So increased CO2 has influenced human activity. Humans have increased the planting of trees in areas burned by wildfires in order to decrease the amount of carbon dioxide. Maybe. Humans have increased the burning of fossil fuels in order to decrease the amount of CO2? No, because that increases it, so that's wrong. Humans have moved to cooler climate regions to adjust? No, we haven't. Humans have decreased the number of dead trees in the forest by using them as fuel. Humans have decreased the number of dead trees in the forest by using them as fuel? Maybe. I mean, does this say anything about this? All right, so I think what I'm going to do is I'm going to eliminate 4, because if you burn fuel, you use the fuel for the number of dead trees, you're actually going to put emissions into the air. So the best answer is going to have to be number 1. I don't really like this question too much, honestly. It's kind of weird. So I'm going to say this is like a 6 out of 10. I don't really like it. All right. Let's go on. In Earth's past, the carbon cycle has changed due to changes in climate that resulted from several different factors. Changes in the sun's energy, the amount of marine organisms that remove CO2 from the atmosphere, and uplift of major mountain chains that have all contributed to variations in CO2. Ice core data provides a record of atmospheric carbon dioxide, which is measured from trapped air and ice, and changes over the last 800,000 years have been shown. So CO2, you could just see recent is pretty high, but it's been high over the course of time. And the Antarctic temperature, you could see, is warming as well. It's at the higher point, it's lower right there. Which claim summarizes the data in the graphs that a change to one system causes another change in another. So I'm saying, if you pollute the atmosphere of CO2, it affects the ice. Increasing CO2 levels cause the Antarctic surface temperature to decrease? No. Variations in CO do not affect the surface temperature? No. Decreasing them cause Antarctic surface temperatures to also decrease? Yes, they're directly related there. Atmospheric CO2 level stayed the same? No. So this one, the answer to 14 is going to be 3, and this question is super easy. And they better give you an easy question after those last couple, because those were stupid. 2 out of 10. Using the rate of climate change in Antarctica for the last 40,000 years, make an evidence-based forecast of how much the temperatures are predicted to change in the next 40,000 years. Describe a specific association impact to one of the system as a result of this change. Make an evidence base of how much the temperatures are predicted to change in the next 40,000 years. Okay, so if we're going to go from here, which is about here, so we're going from like -3, 40,000 years ago, to 6. So we increased by 9 degrees. So if we're going to the next one, we should probably increase to 9 degrees. So if we're going 6 and then add 9, should be 15. So really for this question, you could have said the temperature was going up, or if you went on variation of predictability, you could have said it was dropping. Because the answer key on this one actually says that you could have said anything from dropping 10 degrees to increasing by 12 degrees. So either one of those would have been right. So I'm going to go with my original, which would be +9. And if it's going to warm, the associated impact of that is going to be more ice melting. You could have also, if you had a decrease in temperature, you could have said more ice is going to form. So depending on what you wrote, that could be fine. So based on them giving such a wide range of acceptability to this one, I'm going to say this one's a 5 out of 10. But you have to be able to look at a chart. All right, we're going to go to number 16. Base your answers to questions 16 through 20 on the information below and your knowledge of Earth's space science. Some questions may require the use of the reference tables. Okay, so we got stars and the Big Bang. Our sun is a 4.6 billion year old yellow dwarf star. Okay, that's maybe good to know. It was formed either from matter produced during the Big Bang or from matter released when large stars reached supernova and exploded. This matter, in the form of hydrogen, okay, contracted into a denser gas cloud due to gravity. The temperature of this cloud's core increased, allowing for the fusion of 2 hydrogen nuclei into 1 helium. The mass of this helium is slightly less than the mass of the hydrogen. This difference in mass is the source of the star's energy. Okay. So first off, if I'm seeing life cycle of different stars, I'm just going to show you. We do have a life cycle of stars reference table page. So I don't know if we'll need it. There's actually a ton of star stuff on the reference table. So we'll see. Let's see, model of life cycles of different stars. We have gas and dust. So we have a high mass, a medium mass, and a low mass. So the mass is actually the difference between the 3 life cycles. And it's the same here. You can see the low mass stars versus the massive stars, sun-like stars. It's all about the mass. Identify the factor that determines the lifespan of the sun and the other stars. Boom, done. We already know it. It's the mass of the star. So that was very easy. 2 out of 10. The table below shows some information about different types of stars. Solar mass is the mass of the star compared to the sun. Okay, so like Spica is 10.3 times massive as the sun. The sun is 1. So the sun is our point of comparison. A student created a data table containing information on how stars synthesize common elements through nucleosynthesis. Okay, so check this out. Look, nucleosynthesis. So I don't know if this is going to help us, but we'll find out. Which row correctly identifies all the characteristics for that star? Okay. So carbon to oxygen, helium to carbon, hydrogen to carbon. Are we just picking a row? Yeah, it looks like it. Okay. So first off, let's get the lifespans done, because those are right here. Look. Sun. 4.6 billion lifespan. No, because it's 9 billion. So this is just automatically wrong. Sirius B, 0.23 billion lifespan. That's correct. Aldebaran, 6.4 billion. That's correct. Wolf 359, 4.1 trillion. That's correct. Okay, so we at least got rid of 1. All right, let's go to mass. So high mass, Sirius B, 0.98. That's less massive than the sun, so that's not high mass. So that's wrong. Aldebaran being medium mass, 1.16, possibly. We'll say maybe. And Wolf 359, look, 0.09 solar mass, that's not high mass. So we know this is probably the answer, but let's just see nucleosynthesis. Does helium change directly to carbon? Yes, it does. See? This is the answer. 3. That was easy. 3 out of 10 just because I had to use the chart a little bit. All right, sunspots are areas where the magnetic field of the Earth is 2,500 times stronger than the Earth's magnetic field. Because of this strong magnetic field, the magnetic pressure increases and the sun's surrounding atmospheric pressure decreases. Okay. This lowers the temperatures relative to surrounding areas because it inhibits the flow of new superhot gas to the surface. Sunspots occur in pairs because they have magnetic fields pointing in opposite directions. However, from that year to that year, there was zero sunspot activity. This time period is called the Maunder Minimum. Some scientists also call this time period on Earth the Little Ice Age. Okay. Let's just see what this says. We might have to reread that. Using information from the passage, place a check mark in 3 of the boxes to identify the statements that describe sunspots accurately. Okay. Okay, so a decrease in the number of sunspots is inferred to decrease the temperatures. So since it says up here, some scientists also call the time period on Earth the Little Ice Age, when there was zero sunspot activity. Based on that, a decrease in the number of sunspots decreases the temperature of the Earth. So that is right. The number of sunspot changes each year, occurring in 11-year cycles. So if you look, we're going from, well, we don't know if that's the high. So we'll start at the peak here, being at like 1957. And then the next peak is going to be like 1968. So that is an 11-year cycle. So that would work. An increase in solar output is associated with a decrease in the number of sunspots. No, that would be the inverse of number 1. So it's a direct relationship. So that's wrong. The average number of sunspots has decreased steadily since 1950. So you could see 1950 is here. It's been higher than that. So that's not right. And sunspots are regions of cooler temperatures. That is correct. Because it says it up here. It lowers the temperature. So there's your answers. I think this question's like a 6 out of 10, honestly. It's between using the reading and the graph, and honestly, it's an assumption. To me, this is an assumption that the Little Ice Age on Earth was a period of cooler temperatures on the Earth. Like, I don't know. Like, that's just assumed. I'm assuming that's right. So, yeah, I don't really like that part of it. Maybe if they explained a little more what the Little Ice Age actually was on Earth, it would be better for, like, students. You know, they might not associate that. Maybe they would. I'm not sure. Okay, going on. In the 1920s, Edwin Hubble studied the motion of galaxies. Okay? He found a relationship between a galaxy's velocity as measured from the Earth and the galaxy's distance. The relationship known as Hubble's law. The graph below shows several velocities distance from the Earth and their recessional velocities. So pretty much the further the galaxy is, the faster it's moving. So this is like part of the reason why we know the Big Bang happened, right? So increase distance, increase velocity, right? Okay. Let's see. The relationship between galaxy distance from Earth and recessional velocity graph shows that the recessional velocity of a galaxy blank as the galaxy's distance from Earth increases. This would be increases. So increases proportionally. So 2's out and 4's out. This is evidence for the blank expansion of the universe, where good on B is the same, and suggests that the universe initially was compacted. It was together. And then as a result, this data suggests that the universe is changing at an accelerated rate. That's correct. So 1. This one is about the universe. I mean, a little content knowledge is involved in understanding that the universe is expanding faster, and it used to be, you know, in a infinitely small dot and then expanded over time. So I would say that's a 2 out of 10. Pretty basic. Particles were created as a result of the Big Bang. The first particles were subatomic particles like protons, neutrons, and nuclei of lighter elements such as hydrogen, helium, lithium, and beryllium. This graph shows some information about these particles, the temperature of the universe at the time they were created, okay, and the amount of time after the Big Bang that they were created. Okay, so we got this thing. What the? I think this is torture to read this graph already. I can't even imagine what the question is. I'm gonna just say torture. Why? Why? Based on information from the graph, which table correctly identifies the composition of matter in the universe as evidence for the Big Bang? Oh my gosh. Alright, well, we're just gonna have to check these 4 things. Alright, let's see. From 10 to 100 seconds. So let's just go with that. We're gonna really have to break this down. From 10, right here, 10 to 100 seconds. So from here to here. And then what? Did H and HE decrease? Where's H and HE? H, there's so much hydrogen and helium. This is neutrons and protons. So H, hydrogen, and all these heliums went up. So that's out. Goodbye. All right, that was an easy one. From 100 to 1,000. So now we're in from 100 to 1,000. This section, from here to here. Let's get rid of this line so you don't have to worry about it. Now we're looking there. Did H increase? H increased, then decreased, while HE increased and then remained constant. Oh my god. Let's see if H increased then decreased first. Hydrogen. Hydrogen increased and then decreased. That could work. And then HE increased and then remained the same. That could work. All right, so we like this one so far. Oh, let's just check the last thing. Temperature decreased. Where the heck is that? Temperature. Look, 3 times 10 to the 9th, 1 times 10 to the 9th, 3 times 10 to the 8th, 1 times 10 to the 8th. This is always going down, so that's right. All right, we found a winner. Let's just check the other ones. From 1,000 to 10,000, it's saying protons and neutrons decreased. So from 1,000 to 10,000, look, protons and neutrons decreased. Protons pretty much stayed. Look, protons stayed the same, so that's wrong. And then after 10,000 seconds, BE and LI remained constant. 10,000, look, BE and LI did remain constant, so that could be right. And we got to check the last thing. Temperature remained constant? No, it constantly drops. All right, we did it. Ugh. I mean, the tables weren't that bad, to be honest, but that graph is terrible. Now, and look, I'm zooming in on this in a computer screen. You know, a kid's going to see this on a paper, you know, probably pretty small, and have to deal with this. So that's very annoying. So I would say because of that, I'm going to give this a 6 out of 10. But you saw how I solved it. Like, you got to do it in parts, you know, go one thing at a time. Like, this is going to take a while. This is not meant to be a fast test whatsoever. You have to really slow down and really think about it. Break it up into pieces. Like you know, I've been doing this a long time. My brain cannot possibly comprehend this all in one shot. Like, I can't just look at one of these charts and go up there and just solve it. I'm going to forget. I just go one section at a time. You know, eliminate. It's the only way to do it. All right, base your answers to question 21 through 25 on the information below and your knowledge of Earth and space. You may require the reference of. Okay, New York State Hudson River. New York State's Hudson River watershed covers almost 1,340 square miles and includes 3 different watersheds: the Mohawk River, the Hudson River Estuary, and the Upper Hudson River watersheds. The Hudson River flows south for almost 325 miles from the Adirondacks. Let's look. Here it is, Hudson River. Right there, flowing south, right here, from the Adirondacks. Okay. Here, oh, the 153-mile section from Troy to New York Harbor in New York City is a tidal estuary. So that's Troy. And then New York Harbor, it doesn't label, but it does say Hudson River Estuary. Okay. The leading edge of, here, fresh water flowing south down the river meets salt water pushing in from the Atlantic Ocean. The leading edge of seawater entering the estuary is called the salt front. And where is it saying that is? Right here. So that's where they're saying pretty much is the salt front. But question mark? The salt front moves with the tides, the weather, and the seasons. When there is heavy rain, more fresh water flows into the Hudson River. Cities and towns that take their drinking water from the Hudson River carefully track the salt front as it affects the quality of the drinking water. So they're saying this is going to generally move up or down. Describe how heavy rain events along the Hudson River would affect the location of the salt front. When there's heavy rain, more fresh water flows into the Hudson River. So if there's more fresh water, then the salt front should move south. Because it's going to push it downwards. Right? It's going to move down towards the ocean. Yeah. I like that. The heavy rain causes increased fresh water, moving the salt front south. That question, to me, is ridiculously hard. Fresh water flowing south down the river meets salt water pushing in from the Atlantic Ocean. So the thing for me is that this might seem obvious to you, but the Atlantic Ocean is not labeled on this map. So like the students would need to know where the Atlantic Ocean is. First off, I would say this question so far, I would give this a 9 out of 10. This question is hard. And I know it's secretively hard. But I bet you a lot of people got that wrong. I bet. Alright, let's keep going. The location of the salt front is measured in HRM, Hudson River Mile units. The Hudson River Mile 0 is at the southern tip of Manhattan in New York City. The table shows information about the salinity along the Hudson River for several locations north of New York City, or on 2 different dates. Salinity is measured in milligrams of chloride per liter of water, and the salt front is located where the salinity is 100. So, if the salt front is where it's 100 what is that, HRM? Oh, 100 salinity. So the salt front's here, between 50 and 300, because we're looking for 100. And then it's between 50 and 8, that's here. So it moved, you could see, is this the same locations? Except for Verplank for some reason, I don't know. Let's see what it wants to know. A student makes a claim that the location of the salt front is constantly changing due to the weather conditions. Which table supports the student's claim by correctly identifying the 2 locations between the salt front that was located October? Okay, so I literally just guessed that they were going to ask where the salt front was in these 2 diagrams. So I already solved it. So on October 6th, it's between Piermont and Bear Mountain. And then on October 12th, it's between Verplank and Cold Spring Harbor. So that's wrong. Or Cold Spring. Piermont and Verplank and Cold Spring. This is the right answer. So, like, I feel like I just, having so much background knowledge, I assumed that they're probably going to ask me that. But that's pretty easy. I would say this is like a 4. Okay. An advancing salt front along the Hudson River can affect the quality of drinking water for communities such as Poughkeepsie, which use fresh water from the river as a source of drinking water. For this reason, 2 different environmental groups carefully monitor the salt. Since 10 million people in New York State rely on the Hudson River for clean drinking water, both environmental groups had developed a plan to evaluate the salt front to prevent the salt from entering and drinking water. This $400,000 plan is a budget to monitor and evaluate salt from advancement over the next 35 years, okay? This budget has two components. Allocate $250,000 to predict the salt front location, and then $150,000 to develop a plan to maintain safe drinking water. Okay. Based on evidence in the plan developed by the groups, which explanation correctly describes how the availability of fresh water will influence communities along the Hudson River? Well, it's obviously important. Let's see. Cities along the river will need to spend considerable amounts of money to find alternative drinking water sources as the salinity decreases. No, because if it decreases, then it will have good water. Cities along the Hudson River will need to spend $400,000 to monitor the salt front over the next 50 years. No, because it's over 35 years, so that's not right. This question is so stupid. Communities that use the Hudson River for drinking water will spend $400,000 to monitor salinity and develop plans to purify water if necessary at water treatment plants. Yeah. Communities that use the Hudson River for drinking water will need to spend $150,000 to predict whether the salt front will affect their drink. No, that's for the plan. Are you serious? Why would you put this question? It's stupid. They're just wanting you to re-summarize the reading. I mean, this question should be on an English final. This question's terrible. It's stupid. What a waste of a question. I mean, honestly, it's like a 1 out of 10. It has nothing to do with... It's just a waste. It's complete waste. I could have put a rocks and minerals question in here or something. Okay, let's go on. The location of the salt front and its effective drinking water is not the only issue facing residents along... I mean, I can't believe we're still talking about this salt front. Look how much words we're talking about this salt front. It's so much words. This is the problem. My first gripe with this, like, it's just too long. The location of the salt front and its effect on drinking water is not the only issue facing residents along the river. Between those dates, industries that manufactured substances used in fire prevention and oil insulators called PCBs were found to be toxic to humans and life in the river. By then, the industry located north of Albany had dumped an estimated 1.3 million pounds of PCBs into the river. Once in the river, the chemicals mixed with sediments on the bottom and along the shore. The removal of a dam in the upper Hudson in 1973 further released large amounts of contaminated sediments. So there was already tons of sediment, toxic stuff, dumped, and then they removed a dam that released more bad things. In 1984, the EPA classified a 200-mile stretch of the river as a federal Superfund site that required the removal of PCBs from the river sediment. A 40-mile stretch north of Albany was termed as a hotspot where PCB-contaminated sediment was removed by dredging between... That's just like scraping the bottom of the ocean, pretty much, or the river, to get this stuff out. Between this, the model shows some information on PCBs. Okay. What would you like to ask me about? Oh, more reading. Eating contaminated fish is the... What? Was there a question? Now we're talking about contaminated fish. Eating contaminated fish is the single greatest human exposure to these PCBs. That have been present for 70 years, have accumulated in fish. Advisory not to eat the fish. 2002, the EPA adopted targets of PCB concentrations in fish to be reached by 2021 and 2031. The graph below shows PCB concentration of fish taken from the upper Hudson River and these total targets. Weighted average total PCB in upper Hudson fish. Okay, so essentially in 2016 there was a high amount, and then it got lower, and then it got lower, and then it got lower, and then it got much lower there, so it's the lowest here. And then it got a little higher, and it's saying that's the actual pollution in the fish. The EPA's target for 5 years after dredging was here on this line, and after 16 years was here. So they did not reach their goal. Either way. Yet. So 2016 to 2021, they should have been at 0.4, but they didn't get there. If anything, it's going back up. So they did a terrible job. Based on the model and the graph, which would be the next logical solution that would cause the greatest decrease in PCB levels in the fish? So what should we do? That would be the best. Do nothing? No. Dredge additional areas that still have PCBs and sediment to permanently remove the pollutants from the river? Maybe. Build another large dam where the dam is removed to capture most PCBs before the sediment moves downstream? Too late. Breed larger fish that can remove the water? No, it's just going to eat the fish and they'll be polluted. So the only one that makes sense is 2. This is a terrible cluster, in my opinion. That's a 3 out of 10. Explain how the graph supports the claim that dredging of the river has only been partially effective at reducing PCB levels in fish compared to the EPA targets. So, I mean, we answered that. The lowest it's gotten to is 0.63, and the EPA target in 5 years was supposed to be 0.4. So it didn't make it. The target after 5 years was 0.4. But it only dropped from 1.3 to 0.63. That's the answer. I mean, that was pretty easy. So 2 out of 10. All right, base your answers to 26 to 30 on the information below and your knowledge of Earth science. Okay. The origin of our solar system. The sun and the 8 planets in the solar system formed at the same time. Evidence of their formation can be found throughout the solar system. Scientists have used data from planets, meteorites, and Earth to determine how the solar system formed. Data table lists some information for the 8 planets. Okay, so there's the terrestrial planets. Are those 4? Jovian planets are these 4. And you could obviously see that these have way more moons. Which statement best describes the difference between the terrestrial and Jovian planets in the solar system and the early formation? Okay, so we do have a table we can use for this right here. I don't know if it's going to help us. Terrestrial planets have longer periods of revolution and fewer moons, so we definitely know terrestrial planets have fewer moons. But you could see Mercury, Venus, Earth, and Mars have these periods of revolution, which are way lower than the Jovian. So that's wrong. Terrestrial planets have greater density and longer periods of revolution. We already established that they don't have longer periods of revolution, so that one's out. Terrestrial planets have larger diameters. No, they're way smaller, and you can look here at diameter. So look, these numbers are small, and then these numbers are in the tens of thousands, so that's wrong. Terrestrial planets have smaller diameters and greater densities. Correct. And if you didn't know they have greater densities, you can go... Oh, there's no density column here? Well, terrestrial planets are made from rock, so I guess that's something that you just have to know. And Jovian planets are the gas, so that you had to know. So, I mean, this is just basic solar system, so I would say this is a 3 out of 10. And it's really a 2, but I just gave it the extra point because you did have to know about the densities. Which value would be the most accurate prediction for the period of revolution for Saturn? Can't you just go here? 29.5 years. They want it in days. Oh boy. So you got to do 29.5 years times 365 days. I've got to get my calculator. 29.5 times 365, 10,767. So it's going to be 2. Now, I'm going to put a star next to this. So far, this is the only time we needed a calculator. We're 27 questions in. That's the only time we needed a calculator. Otherwise, this was really easy. I'm going to be giving this a 2 out of 10. All right. Meteorites on Earth have been helpful in reconstructing the history of our solar system. So right now, I'm just showing you what I'm going through my head. Decay rate of uranium-238. I'm going right to the chart. where I have that stuff. Keep going. Go, 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 right here. So it says already uranium-238. I'm right here. I don't know if I need this, but it's just triggering in my head that, oh, I'm on this radioactive dating chart on the reference table. This is page 15. Okay, a sample of the meteorite was tested and found 50% uranium-238. Use evidence from the graph to make a claim about how this dating can be used to construct an account from when the Earth formed. Okay. We need to know when the Earth formed. So I already know that, but I think if you look here, look, estimated time of origin of Earth, 4.6 billion years ago. So it does give that to you right there on the reference table, page 6. And then if you look at 50% uranium, and you go right here, look, boom, it's about 4,500 million, which is 4.5 billion. So we could say at 50% uranium would take 4.5 billion years, and the Earth is estimated 4.6 billion years old. That's it. So, I mean, if you didn't know the Earth's age, that could be an impossible question to get. But if you did, this is like I would say a 4 out of 10. You did have to know how to read the graph. So at the end of the day, we did not need this, right? Does this help us at all? No. Okay. All right. Throughout the history of the Earth, meteorites have created impact craters on the ocean and continental crust. However, of the approximately 200 craters confirmed on the Earth's surface, only about 20 are located within the Earth's ocean crust. This is surprising since 70% of the Earth is covered in water. It's suggested by scientists that the movement of the plates may play a role in the lack of evidence of impact craters observed in the crust of the ocean. We got the approximate rates of movement are indicated in centimeters per year. And we got 2 impact craters labeled. So there's one, and here's another one. So this one's in the ocean, and this one's on the continent. You could see this has a 2 centimeter per year rate of removal, and this is 7 centimeters per year. So essentially, they're saying this crater, since it's connected to this plate here, is moving this way, and it could get subducted. It's getting subducted at a faster rate than this would be destroyed. Okay, which statement most accurately identifies why evidence of the crater A will most likely not be preserved for as long as B? We just said it. Impact crater A is located on a faster moving ocean crust, will be destroyed by subduction. That's literally the answer. So I was able to just get that by looking at the chart, but again, I have like crazy background knowledge, so you might not have gotten that, but based on reading that sentence, you could have seen that be the case. Let's just see the other ones. Impact crater A is located on a slower plate and will be subducted before B. No, because it's not going to be subducted before it if it's on the slower plate. A is going to be destroyed by hot molten rock at the mid-ocean ridge. No, the mid-ocean ridge is here, so it already passed that point. And impact A will be destroyed by eruptions from the volcano. No, it's going to go underneath them. So that was pretty easy, honestly. So I'd say this is a 3 out of 10. Earth systems do not operate independently. For instance, changes in the ocean's temperature can influence atmospheric temperatures. A similar coevolutionary process occurred in the Earth's early history when oxygen levels were transitioning from the ocean to the atmosphere. Okay. Oh my gosh. Okay. I'm not even going to look at this chart yet. I'm just going to see what it wants to know. How many questions are for this chart? Just one. One question. Okay. Identify the process that caused the oxygen levels in the oceans and atmosphere to change. Then construct an argument based on the evidence that describes how oxygen levels change in the oceans and atmosphere and how these changes lead to a coevolution of life on 2 Earth spheres. Oh my gosh. Okay, let's take this step by step. The process that caused the oxygen levels to change. Let's see. No oxygen. Oxygen levels. Boom. Done. Photosynthesis. Okay, so there's my process. Another photosynthesis question. Why? Okay. Then construct an argument based on evidence that describes how the oxygen levels change in the oceans and atmosphere. So let's do that first. So oxygen, look, they rose. And then they rose in the ocean. So we'll just start with that. After photosynthesis, oxygen levels rose in the ocean and atmosphere. And that's the first part. And how these changes led to a coevolution of life on two spheres of the Earth. Well, greater diversity started forming. There's more forests. So we could say there's more forests. And then we could say there's more different fish. There are more forests forming. And more, we'll just say more diverse life, because that's the biosphere. So we could say more forests and more diverse life. I think that covers everything. Yeah. I like it. I don't know. You know what? I'm going to call this a 5 out of 10. The reason why I'm giving it's really probably a 3, honestly. But now, in my opinion, everything from this point on is going to get an extra 1 or 2 points because of how much test fatigue is probably going to be setting in. Now, I'm on the large type font. I mean, that's just for the video, but I'm only on page 32 out of 56. So look at all this stuff that we have to go. So if you're a student taking this test, everything probably after question 25, maybe before that, is going to start being harder because you're going to start getting tired of reading. It's test fatigue. It's a real thing. So everything's now going to get a +1 point no matter what. All right, base your answers to question 31 through 35 on the information below and on your knowledge of earth science, and you might need the reference table. Okay. Mining and use of lithium. Lithium is a highly reactive alkali metal that's used in the manufacturing of lubricants, pharmaceuticals, glass, and rechargeable batteries. The demand for lithium has grown because lithium is often used in modern electronics like phones, laptops, and electric cars. Okay. So let's underline that. Okay. When in operation, a battery electric vehicle produces 0 emissions. The infographic below summarizes the average amount of emissions measured in tons of CO2 associated with the manufacturing and use of 3 different types of vehicles during their lifetime. Okay. So this is 3 different types. So we have battery electric, hybrid electric, which is electric and gas, and then internal combustion engine vehicle, which is just your classic gas vehicle. And then it tells you the total amount of emissions, I guess, associated with the manufacturing. So you could see 41. So the battery electric has the least cost to emission. You can see the battery actually costs a little bit to manufacture. And then the hybrid is second, and the engine combustion one is third. Okay, we knew that. Which has the smallest negative impact on the environment? Okay, it's the battery electric. And the reason why, evidence from the infographic, 41 TCO2e is the lowest total. I mean, that's literally all you pretty much have to say. And that's so easy. I would say that is a 1 out of 10. Literally so easy. All right. The data below summarizes the originally proposed toll rates for motorists entering New York City by Port Authority bridges and tunnels from New Jersey. Vehicles eligible for the Green Pass discount include plug-in hybrid electric vehicles and battery electric vehicles. Okay. So this is tolls, and it has to do with Green Pass. So you could see it's cheaper if you have the Green Pass. I mean, it's the same at peak. But off-peak is much cheaper. Vehicles entering New York City add pollutants to the air in a congested urban area. Describe the economic benefits to motorists who drive Class 1 and Class 7 vehicles. See, this is Class 1 and Class 7. During off-peak hours that qualify for the Green Pass toll rate. So let's start with that part. Economic benefit. This is so easy. Less pollution. Done. That's... Oh, wait. That's environmental. That's not going to work. Economic benefit. Less money. Wants and also discuss how the wants and needs of society are affected by the toll plan. So they're pretty much incentivizing you driving an electric vehicle. That's all. So wants and needs of society are affected by the Port Authority toll plan. So you could say something about driving an electric, or we could just say driving a Green Pass eligible car is cheaper for the toll and provides and pollutes the environment less. That's it. That was easy. 3 out of 10, I guess, just because you have to read a chart. I honestly, people were saying that they had a problem with toll rates in this test, and I mean, yeah, it's kind of weird, but I mean, they're just trying to relate, you know, polluting the environment with cars to tolls. So they're giving a real life situation where this is occurring. I don't think this is a big deal. People were saying like this was a weird question, but I think it's pretty straightforward, honestly. I don't see a problem with this. There's so much worse issues besides this toll question that we've seen so far, as you remember. So I thought that was fine. Whatever. That was like a whatever. All right, lithium is currently sourced from surface mines or underground brine reservoirs. Okay, so they pull lithium from mines or brine reservoirs. Lithium ore extracted from open pit mines is dried in fossil fuel burning kilns. Okay, so if they mine it, they have to dry it using fossil fuels. The underground reservoir brine method uses evaporating ponds and solar energy to collect lithium from brine water having a high concentration of various salts. So they're pretty much saying like this brine method is better, like less polluting, essentially. Okay, the table below shows information related to these methods. Okay, so we're going to mine lithium. Emission of CO2 from the mine is high compared to the brine method. Use of water. And then use of land. So you could see water and land are way less too. Okay. Which table correctly summarizes the benefits of extracting by mining or the reservoir brine method? So you could see this uses way more water and more land. Okay, so it's better for carbon dioxide, but it's worse for water and land. So we want this one. Mining has less use of water and land, but higher emissions. So 33 is going to be number 4. So again, this question is really easy. I mean, there's a little reading involved, so let's just call it a 4. All right, lithium production has impacts on land and use in the Atacama region of Chile. The photograph shows solar evaporation ponds at a brine extraction processing facility. Okay, so these are the brine extractions. They're doing the lithium. Okay. Shows some information. Over the years, we have produced way more lithium. Okay. Which statement correctly identifies the changes to the lithosphere that were needed for the brine lithium extraction between 1995 and 2022? The amount of land needed increased. The amount of land surface needed for evaporation ponds was lowest in 1995. Does it show a chart for that I missed about land usage? Where is this? It just says lithium production. So are we going to assume that if you're using the brine method, so we're going to say if you're using brine, that means more land and water is going to be required. That's what we established already. So we're going to say in 2022, they need more land and water. The amount of land surface needed for evaporation increased consistently. So we're going to, so no, because right there it didn't. So that's not right. Oh, from 2005 to 2010. Yeah, no, that wouldn't be right. The amount of land surface needed was lowest in 1995 and greatest in 2015. No, it's greatest in 2022 and on. So that's not right. The amount of land surface needed for the ponds increased between 2015 and 2022? Yes. The amount of land needed only decreased from 2010 to 2015? No, because it decreased there too. So this is easy, but remember, you had to know from the reading that more brine production would be more lithium production with this way would require more land. So you needed to know this from the reading to then get that. So I'm going to say that's one harder than the last one. I'll call this a 5 out of 10. Okay, going on. The Andean flamingo, a bird native to wetlands in the Atacama region of Chile and other locations where lithium deposits occur, is listed as a vulnerable species. Okay, great. So it's just it's like endangered almost. The model below shows some information about the brine method. The graph projects changes from 2020 to 2060 in that area due to the mining. Let's just go from left to right. Ready? Extraction of brine from beneath the wetland. Okay, that happens. So there's your flamingo. You're pumping the brine into here and putting it into these evaporation ponds. Okay. So you're left with the lithium as precipitates, and then your waste goes underneath it. Okay, and then you transport the lithium out to a production plant, and then you make your battery. So you're pulling water from an aquifer up, out. Projected wetland losses. Look, percent of wetlands remaining. So look, their wetlands is going to be gone. They're losing wetlands at a dramatic rate. So this flamingo is going to die. That's probably where they're going with this. So even though, so this is important to know, even though the brine method is going to be less pollution, you're destroying wetlands. That's your feedback, right? Because then you're going to destroy the wetlands, which kills vulnerable species. Okay? So which statement correctly identifies how the processing and management of the salt saline brine for lithium production negatively impacts the flamingo habitat? Pumping of brine from the evaporation ponds adds to the wetlands? No. Pumping of brine from the aquifer reduces the water that would be available? Yeah. Evaporation of water reduces the water that would be available from the wetlands? That's not in the wetlands. Evaporation of water from solar evaporation ponds adds water to the wetlands? No. So I think this is going to be your best bet. 2. I'm just see, I would put this as a 5 out of 10, but remember test fatigue, so I'm going to say this is now a 6 out of 10. Because honestly, it'd probably be between 2 and 3. Because students might think, oh, you're evaporating from the water from the aquifer, but you're not evaporating from there. You're evaporating from the ponds. Okay. 36 through 40. Oh, here's the other one that everyone was complaining about, the ghost forest. Okay, let's read about ghost forest. Ghost forest is a term used to describe a group of dead trees that remain standing. Okay. Ghost forests often form due to environmental change or natural disasters that impact coastal forests. As sea level changes, the invading seawater can advance and overtake the fresh water that many tree species in coastal forests need to exist. So the salty water slowly poisons living trees, leaving dead and dying timber. Ghost forests can be found in almost every coastal state of the United States. Well, that's terrible. So it's essentially using the salt water as drinking instead of the fresh water, which is bad for the tree. Okay. Coastal forests serve as efficient carbon sinks, collecting and storing carbon. Yeah, so they're pretty much saying, so increase salt water is less trees because the trees are dying, which means more CO2 in the air because that CO2 is not being pulled in by the trees. So, and what is this from? As sea level changes. So we could say like increase sea level would be more salt water, less trees, more CO2. Coastal forests protect against erosion, buffer storm surges, and provide wildlife habitats and ensure water quality and quantity. As the saltwater intrusion intensifies, the supply of the wood will also shrink, harming the economy of rural areas that depend on it. Okay. So that's fine. The graph below shows some information about CO2. Great, so you could see CO2 is going up, and sea levels going up. So that's going to relate to our forest issue. In addition to increased CO2 emissions, which row correctly describes the factors and their effect on coastal flooding in areas where the ghost forest land cover has increased from 1920 to 2020? So 1920 to 2020, let's see. 1920, we're negative 0.1, negative 0.3. And we're going to 2020, which is 445. So this pretty much increased by 445 about, because the negative 0.3 doesn't matter. It's negligible. And then this is going to be negative 125 going to like 75. So you can figure out that's 75 plus 125. Now this might be, so this changed by 200 millimeters about. So this might be something you would need a calculator for again. So that's 2 questions so far for a calculator. So let's see. Total change in temperature anomaly. So it's saying from 1920. Oh, I'm sorry. I didn't do this right. So these are 2 different axes. There's the CO2 there. There's a dash line. I didn't even notice. And then there's the temperature. So this went from negative 0.3 to about 1.0. So that's why this total temperature change is 0.9. So this is all... So it went up by 0.9. It didn't drop by 0.9. So that's out and that's out. The sea level anomaly. So this is going to be from... Here, that we did 200 millimeters. So now we're here, and we eliminated this one, and then flooding increases. So this 36 is going to be 3. So that almost tricked me, because I didn't see that these were 2 separate lines with 2 separate things. Look, atmospheric CO2, the solid lines, that numbers, and the dash lines are those numbers. But this being 0.9 made it not make any sense. So I would say 5 out of 10 normally, test fatigue, added 1, 6 out of 10. All right, going on. The infographic below shows the predicted development of the ghost forest in coastal areas near residents from 2020 to 2100. Brackish water is a mix of fresh and salty water. Okay, great. So let's see what's happening here. So there's a well. We see the fresh groundwater is bringing up from the well. And the 2020 is here for the water table. That's the height of the water underground. Salty groundwater. Great. So this is saying what changed. This guy changed. So you can see that tree died because there's more salty water, I guess, coming in because the sea level went up. Oh, we have another picture. Sea level's going up more. Now we have more brackish groundwater, which is going to bring up the well water and give salty water into the residency. And this is because sea level is rising. And look, it even destroyed this side of the house too, because the water table is like leaking under here, I guess. Identify one natural resource that'll be affected by the rise in sea level. Oh, okay. So we said timber. Remember? They said that since the ghost forests are going to not be able to, the forest's not going to be able to grow right, that's really going to affect the timber. Effect on human activity, less supplies. Change how the availability of this resource will affect human activity. Less supplies to build. I feel like that's good. Right? Yeah, I like that. So that was pretty easy, honestly. So 3 out of 10, but +1 for test fatigue, 4 out of 10 difficulty. All right, 38. A student makes the claim that the amount of living forest acreage will decrease as the amount of ghost forage acreage increases. Yeah, we said that. So obviously, if there's more ghost forest, there's less living forest. Which impact to an Earth system will most likely occur? The increase in wetland area will decrease humidity. No, nothing to do with that. The loss of ground vegetation, yes, will cause an increase in runoff and erosion. Yeah. As high tide water increases, the local climate will cool. No. New species that live on the dead wood will increase the biodiversity. No. So I would say 38, the best answer here is 2, and this actually is said in the reading. So again, I would say this is a 2 out of 10, but +1 for test fatigue, so we'll go with a 3 out of 10. That's a complete reading question. That was easy. Okay, the model below shows the effects of subsidence, this is sinking, in the creation of ghost forests as a result of an earthquake that occurred. So, ready? Big earthquake. The forest floor literally dropped. And that causes the floods to be higher, essentially, because the floor dropped. Use the model to compare the temporal, that just means over time, of the land subsidence associated with the earthquake to the temporal scale of lab subsidence due with the development of a ghost forest. Okay, so temporal. This is how long things take. So if you're comparing an earthquake to the development of a ghost forest, this is going to happen. The earthquake happens instantly. It's very fast. A ghost forest happens slower. That's an over time thing. Temporal scale of land subsidence with an earthquake, this happens fast. You could say in a short time. And then over of a ghost forest, this is going to happen over a long time. You could even say a longer time, just so you can keep it, comparing them to one another. That's it. I thought that was easy. So 3 out of 10 normally, +1 fatigue, 4 out of 10. Okay, 6 proposed solutions for reducing the expansion of ghost forests are above. So we want to prevent the expansion of ghost forests. Fortify seawalls with concrete. That could be a good thing to do because it's going to prevent the seawater from coming in. Use sand and soil to create dunes with grasses along the coast. That could also be good. Limit development along coastal wetlands. Limit development. Probably that's a good thing too, I would say. Install sand fencing to reduce loss of sand. Okay, that could be good, I guess. Preserve and restore the biodiversity of vegetation. Yeah, we need the vegetation. Install tall rock walls. Okay, so which Three solutions reduce the expansion of ghost forests and would most likely be accomplished with minimal environmental impact and maximum aesthetic value. So we want not that much to destroy environment, and we don't want it to look bad. Maximum aesthetic value. We want it to look good, and we don't want to destroy the environment. Don't mess up environment. So we need that. So concrete, that looks bad. Use sand and soil to create dunes with grasses. That sounds like it'd be pretty and good for the environment. Limit development along coastal wetlands. Let's just say anything with 1 is gone, right? So 1 and 2 are out automatically. We don't, this is, so let's just say no, maybe. Limit development. Okay, maybe the wetlands are nice. Install sand fencing. That looks ugly. So let's say 4 is yucky. That's not even in our 2 last choices. Preserve and restore biodiversity. That's good. 5 is good. Install rock walls. That sounds bad. So we like, so far, 2, 3, 5? 4? Yeah, I mean, that sounds good. I hate this question. I don't like it. I think it's a little bit subjective, meaning it's like up to the opinion. Because for me, right, if this was my city, I would say if there's a really good solution that's effective, like building some sort of walls and that's going to really prevent the ghost forest, I don't care about maximum aesthetic value. I just want to save the environment as much as I can, you know, save the water quality as much as I can. So I would think that, you know, I would want to do that. I just don't like this question. It's bad. And yeah, I don't like it. So I'm assuming a lot of students will get this wrong. So I would say we're talking like a 7 out of 10 difficulty plus 1 test fatigue, 8 out of 10. This one's pretty hard. I bet you a lot of people get that wrong. All right, going on. So by the way, the ghost forest thing, I didn't think that was that bad. That was fine. That was interesting. All right, base your answers to question 41 through 45 on the information below. Human impact on Earth. Okay, here we go. You see, even I'm getting like, whew, all right, here we go again. You know, it's too long. Honestly, they should have ended the test already. Like 40 questions. Done. By this point, most students are checked out. So I would say these last 10 should have been removed. You know, it's even taking me a long time to even go through and explain this, and I have all the background knowledge that I have, so. Yeah, okay, let's keep going. 41 through 45. Global human population has increased dramatically in the last 50 years, which has increasingly stressed Earth's natural resources. Great. This has created challenges in the management of those natural resources while also creating opportunities to find solutions. Great. The En-ROADS simulator is an online tool that allows users to manipulate variables in order to see their effects on climate change. A student used this simulator to estimate the global temperature change by 2100 if we didn't change anything to the current conditions. The graph shows the result of the simulation. Simulation 1 shows the possible outcome of greenhouse gas net emissions and the associated atmospheric global temperature change under current conditions. Simulation 2 shows the possible outcome of greenhouse gas net emissions and the associated atmospheric global temperature change due to a different set of computer input conditions. Okay, so they're pretty much saying, ready? If we don't change or do anything different, bad. If we do change, not as bad. We're still generating a net increase. But remember, the Earth naturally goes through warming and cooling cycles. So there is a chance that even if we were to perfectly remove every greenhouse gas emission on the whole planet, in the whole world, we were to emit 0, there's still a chance that the Earth would warm. So we know this to be the case. So this might be, but this is clearly better, right, than this, 3.3 to 2.5. And let's see what we did here. Increased rate of tree planting, decreased rate of deforestation, decreased rate of greenhouse gases, decreased rate of population growth. So it's saying we have to stop having children, or at least less. So less humans. Okay. Based on the information, which row in the table below correctly matches both the method of managing natural resources and the resulting effect on human population, greenhouse gases and biodiversity beginning in 2020? Replanting forests? Did it say anything about that? Yeah. So 2020 here, right? 2020 here, up. So at this point, we're going to start dropping. So we need to do these things. Method of managing natural resources. Replanting forests. The effect on human population would be positive. The amount of greenhouse gases would decrease. The effect on biodiversity would be good. So that seems like it would work. Replanting forests, positive effect for us. No change in the greenhouse gases? No, it's wrong. Decreasing deforestation. So that's saying cutting down less trees. Is that good for us? Probably. Amount of greenhouse gas, no change? No. Positive effect on biodiversity? Yes. And not cutting down trees would not be negative for biodiversity. So 41, the answer is 1. This has reading involved. It's a 4 out of 10 plus 1 test fatigue. This is a 5 out of 10 question. Okay. The graph below shows some different types of fossil fuels. Okay. Natural gas, oil, and coal. And this is saying fuel consumption in terawatt hours from 1900 to 1922. Okay, and then estimated years of fossil fuels left after 2020. We have a lot of coal left, some oil, and some natural gas. Based on the information, which statement correctly identifies the relationship between the management of fossil fuels since 1950 and the future sustainability of these resources? Okay, so it's just like draw a conclusion. All right, let's go. The yearly consumption of fossil fuels has increased by more than 6 times, and the production of some types of these resources is not sustainable beyond 2150. Okay, so this is going to be a calculator question, first off. So what I'm going to do is we're going to figure out, this says 139 years after 2020. So I'm going to do 2020 plus 139 years. So this is 2159. So coal is good until 2159. Technically. Oil is going to run out in 2020 plus 57, according to this. So this is only going to last till 2077, and this is going to last from 2020 plus 49, which is 2069. We're going to run out of natural gas, according to this. So now what's it say? The yearly consumption has increased by more than 6 times. So is this yearly consumption? And this is saying since 1950. So let's see, ready? 1950. So this is going to be 10,000 or 20,000 times 6. Let's just go high end. 20,000 times 6 is going to be 120K. So yeah, it has, well, actually in 2020. Yeah, so that is true. It is a 6x increase. And the production of some types of these is not sustainable beyond the year 2150. I mean, I guess. Let's go on to the next one. The consumption of fossil fuels has increased by more than 10 times since 1950? No. The yearly consumption of fossil fuel has doubled? Way more than that. It is 6 times. And the production of some types of these is sustainable for the next 30 years. They're all sustainable for the next 30 years. And then this one says it's tripled for 30 years. So 42, the answer is 1. This is hard. I'm just going to say this is a 7 out of 10 with test fatigue, so we're going to make it an 8 out of 10. I thought that was hard. Because you have to literally do this math based on 2020, and that alone is very hard. That would be hard for a lot of students to do. And then you have to estimate this and figure out how many times higher it is here. Come on. I would actually, I'm going to amend this. I'm going to say this is actually an 8 out of 10 normally, 9 out of 10 test fatigue. I bet you a lot of kids would get this wrong. It's just too much. Too much. This is hard. too much. I mean, unless there's a different way you would do that, but that's how, I don't know how else you would do it. All right. The table below shows some information about arable land from 1960. Is that how you say that? Arable? Land from 1961 to 2016. Arable land is land that can be used for growing crops and supporting livestock. Okay, so it's good land. Just say it's good land. Okay, so we could see, look what happened. Boom, 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 boom. Okay, now, so over time, worse land. The land is worse. Based on the graphs, which statement provides evidence to support that the claim that increased consumption of fossil fuels caused a change in the amount of world arable land per person? Well, clearly it's down. The temperature increase, which increased soil evaporation and increased the amount of... No, we're not increasing arable land, so that's both out. So did the temperature go up with decreased soil evaporation and decrease the amount of land? So I'm guessing if you soil evaporation, this is the issue here. If the if soil evaporation is going up, the land, I'm guessing the crops would be less able to grow because you want the water in the soil. That's my guess. So yeah, look, this is why. If you're increasing the temperature, you're increasing evaporation. Because heat, something more hot is going to increase evaporation. So 4 has to be the answer. Temperature increase, which increased evaporation and decreased the amount of land. So 43 is 4. So that, getting this to this with the evaporation, with the heat, that's the link you would need to get rid of these 2 and 4. So I would say that's a 5 out of 10 plus 1, so that's a 6 out of 10. These, I have to say, we haven't really had any less than a 5 recently, so this is kind of harder. All right. The Cheetah Conservation Fund, CCF, is a nonprofit organization that is working to ensure the survival of the cheetah, okay, and its habitat. Okay, the central part of this African country was once a mixed woodland savanna. However, overgrazing by livestock, being cattle raised for meat, hunting of the elephants and rhinos, and removal of trees has changed the landscape to be dominated by thorn bushes. This restricts the ability of animals to hunt. CCF harvests these thorn bushes to make bush block, a miniature log which can be used as a biomass fuel source. So essentially, they're trying to take away the thorn bushes for the cheetah, and then they're taking the thorn bushes and using it as fuel, which I'm guessing they're burning it because it's a log, right? All right, describing the manufacturing of the logs addresses a problem in this Nambia place. So, since we are raising the meat, it's removing the trees. So we're removing all the trees, which is a problem for the cheetahs. So how manufacturing of the logs addresses the problem? Explain how these logs benefit the cheetah population. So how the manufacturing of the logs addresses a problem. We'll say human activity caused thorn bushes to invade the space of the cheetah. And how is this going to benefit? It clears the thorns for the cheetah to hunt. So this is like a weird English question, honestly, if it was, because this actually required no background knowledge whatsoever of this course. So I think this is a waste of a question. I would say it's a 5 out of 10 question plus 1 test fatigue. So I'd say it's a 6 out of 10, and this is a waste of space. This 44 question, like why? Let's see if 45 makes up for it. Increasing the use of biomass is one of the many actions that they're taking to reduce the rate of climate change. Which additional solution, if increased, could be used along with biomass as another renewable energy source? So when you think renewable, we want like solar, wind, water, things like that. So it's going to be 3. And drilling, mining, and burning, that's all non-renewable things. So 45 is 3, and that is so easy. I'm going to say this is a 1 out of 10. It's a really easy question. Okay, base your answers to 46 through 50 on the information below. Great. Why did they even write this? I mean, they could have just wrote like this part. They don't have to say this every single time. The whole test might require it. And by the way, I don't think we barely used the reference table at all. Tectonics of the Hawaiian Islands. The Hawaiian Islands are situated near the center of the Pacific Plate and are volcanic peaks representing a history of volcanic eruptions. Oh, speak of which. Okay, so let's go here. Here we are. In the Pacific Plate, right? The island of Hawaii is over a hotspot where magma source pushes upward, creating active volcanoes. Great. The island of Hawaii itself is still being formed at Mauna Loa and Kilauea volcanoes, both of which are currently situated over the hotspot. Loihi, an undersea volcano, also sits above the Sorry, I'm pronouncing all this wrong. Also sits above the hotspot and will likely become the next Hawaiian island. The other islands in the chain are extinct volcanoes. The map shows the formation of them, varying the age of the bedrock. The model shows 3 stages over the hotspot. Okay, let's look. So there it is, and we're here. Yeah, it's like a little conveyor belt. So this is currently where the hotspot is, which means you could see the ages, right? These are older. So this one used to be here, right? And then it's moving this way. So the plate is literally moving that way. Okay, which table correctly pairs the Earth process with the feature? Okay, so we want, for Hawaiian Islands, we want to make volcanoes make rising magma. It's 2. I mean, this question's so easy. I would say this is a 1 out of 10 plus 1. Test fatigue, it's a 2. Student makes a claim that the motion of the plate could be used to determine the pattern of ages. Yeah. Use evidence from the map to describe the relationship between the pattern of the ages of the island and the compass direction that we are moving. So, pattern and ages. So, as you move northwest, age increases. The plate is moving northwest. That's pretty much all you have to say. That's so easy. So 2 out of 10 plus 1 test fatigue, 3 out of 10. Oh, we're almost done, guys. 2 more questions. So distance from hotspot and age. Yeah, it's literally the same exact. 5 million years old is the furthest away. Right? And Hawaii's on the hotspot. 2 samples of the crust were collected between some of the Hawaiian Islands. Data for samples X and Y is shown below. X is 500,000 and 90. So let's go look at these. 500,000 right here and 90. So it's like here. Ish. And then, oh, it says approximate. So it's about there. 2750, which is there. And then 275, which is here. So it's here. Between which islands were they collected? Okay, so this is going to be X and Y. So X is between Hawaii and Maui. And Y is between Maui and Oahu. So it's 3. That was very, very easy. 1 out of 10 plus 1 test fatigue. That's a 2. All right. The models below show the history of the formation of the present-day Maui. Okay, so evolution of Big Maui. So essentially, all these little islands were close, I guess. Evolution of Maui from Big Maui. Okay. So they separated. So it was here, and now we're separating the pieces. Based on the models, which table correctly identifies the spatial change, so that's a distance. The temporal change, that's over how long, and one possible process that contributed to the evolution of Big Maui. So look, land above sea level, land, oh, so that's what's happening. So it's, the water level is covering a lot of part of the island. That's probably part of it. So it's definitely sea level rise because it says it in the key. So we don't care about that one. It's not sinking. And sea level drop is not happening. Was it really that easy? Does this take 1.2 billion years? No. That can't be right. So I jumped to conclusion there. So it's definitely going to be 1.2 million years. So it's... Oh, it technically could be sinking. So this might be the answer, because it's definitely 1.2 million. Look, 1.2 million is right there. So this is out, and that's out. So, I mean, just based on that, it's 3. So that was actually so easy. So I guess it is sinking, which news to me. But just by the year, this was a 1 out of 10 with a 2 out +1 test fatigue, which is probably the reason I picked that out of my test fatigue. All right, guys, we made it. It's going to be the last question. The photographs below show some shoreline locations on the island of Maui. Human development along the shoreline has impacted coastal regions. Scientists designed solutions to reduce this impact. Okay, so we have a shoreline collapsing. And then what? Oh, they put sandbags there. Okay. Is that a surfer? Oh. And then let's look at 3. Oh, and they put a wall. Identify the problem being addressed in the photographs. It's erosion. Describe how the solutions shown in 2 or 3 reduce the impact of human development on natural geoscience processes that occur in coastal regions. Okay, the problem is erosion. How solutions reduce impact. The wall prevents the water from removing areas of the coast. And that's literally it. That was easy. Maybe 3 out of 10. That's even, I would probably 2 out of 10 +1. We'll go 3 out of 10 for that one. All right, we did it. That is the whole test. So my thoughts, I'm gonna, over the years do these all the time. So my thoughts, too long. We'll see if they fix it over time. Not enough reference table. Not enough, we'll say, like, range of topics. It's too much like human impact, environmental sort of thing. We'll say, like, some torturous graphs and diagrams. Too much reading. But really, like, this goes with the too long. Other than that, honestly, it was fine. My overall, if I say overall difficulty, honestly, if I would say overall difficulty for a regular old student, I would say this was pretty hard. So I'm going to say this is like, I would say this is like trying to really think about this. Definitely above an 8 out of 10. We'll call it the difficulty of this is like an 8.5 out of 10, which is, for me, this was a hard test. Well, I hope you guys got something out of this video, especially if you stuck with me through this whole thing, because this was intense. If you took this test, I hope you did well on it. Let me know in the comments how you did on this test, or if you're just using this as practice, let me know how you did. I'm interested. And if you have any comments about anything I said, about which questions I thought were hard or easy, or you agree or disagree, definitely let me know. All right, I'll catch you guys on the next one. Later.